Hello, sleepy voyagers. Tonight, your journey slips into the deep, the far-off world of Neptune, the distant dreamer of our solar system. Wrapped in twilight and swept by the fastest winds known to science, Neptune drifts through space with a hush that calms every thought. Before we begin our descent, tap like, so this journey can find you again, and subscribe to join our crew for nightly voyages. Drop a comment with where you're listening from and what time it is. I love seeing our galaxy of listeners glowing quietly around the world. Now, take a moment to dim the lights, lower your screen brightness, and, if you like, turn on a soft fan for that steady hush beneath the silence. This isn't just a story. It's your stillness, unfolding beneath a planet where even storms seem serene. When you're ready, close your eyes. You've arrived at Neptune. You arrive without a sound. Neptune hangs beneath you, a slow-moving ocean of blue, and the stars look closer than they've ever been. You're the dreamer in the story, and the planet is ready to carry your thoughts away. We descend, unhurried, through methane-tinged clouds. Lightning brightens a distant layer, fades, and leaves velvet dark behind. The ship feels each wind pulse as a quiet heartbeat. Past the faint rings, Triton waits with breath like geysers that lift and settle. Stay with this gentle arc and let the journey's rhythm replace your own until sleep finds you, steady and sure. Why do stars look sharper as you near a world bathed in blue? You drift above the haze line where the planet's glow thins into a soft rim and the dark stretches clean and deep. You hold your gaze on a field of starlight. The edges feel crisp, the pinpoint steadier than you expect. Your ship hangs in a quiet zone where brightness drops and contrast climbs, and the view changes with it. The sky is not brighter here. The sky is better at being dark. Space should feel the same everywhere you think. Empty is empty, yet your eyes tell a different story. Here, the brightness that usually washes the background is missing, and the starfield settles into fine detail. A calm edge runs through your vision. You start to notice the quiet logic behind it. At this distance, the flood of sunlight is not a flood at all. It is a thin stream. The sun is far, about 30 times farther than Earth, and its light weakens with distance. That loss follows a simple rule. As distance grows, brightness falls with the square of that distance. Out here, the daylight is faint enough that planets, rings, and dust don't throw as much stray light around. Your instruments show a darker canvas, and your eyes adapt to it. With less glare to scatter through the optics and the thin haze, stars sit on the black like grains of salt on slate. Even the planet's faint rings benefit from low glare. When astronomers mapped Neptune's rings and subtle arcs with advanced space telescopes, the weak sunlight and dark backdrop helped those thin structures stand out. In this same low-glare realm, starlight holds its shape. Your pupils are wide. The retinas settle into scotopic mode. The result is a steadier star, a cleaner point, an easier focus. You hover where the upper haze lifts. The air here is sparse and not very reflective. Scattering off a thin veil produces less of the milky wash that brightens a sky, so there is little to blunt the contrast. Your eyes slow down. The ship's displays dim until they barely glow. You become a better detector, purely because the world around you is willing to be dark. The blue itself plays a role. Methane in the air removes much of the red and near-infrared light from the sunlight that filters through. Absorption bands in the 600 to 900 nanometer range bite into the warm end of the spectrum. With less red leaking upward, the remaining scattered light is shifted cooler, and that deepens the planet's blue while keeping the sky around you softly dim. The effect is not a coat of color laid on top, but a filter that edits the light before it reaches you. You notice another small thing. The ship's window rims and panels reflect less because the external light level is so low. Fewer internal reflections mean fewer halos and flares to bleed into your view. Every small reduction compounds and the stars profit. Your head rests back and you watch a tight cluster resolve into distinct points you might miss closer to the sun. It is not silence alone that clarifies the sky. It is the lack of brightness, the thin air, and your adaptation. Out here, stray photons have fewer paths to your eyes. The upper haze is too slight to throw a wide glow across the dome. Your craft's cameras confirm it, logging star counts that rise as the background level falls. What feels like magic is a change in the signal-to-noise balance, and right now, the signal is winning. You drift a little lower, skimming the border where haze begins to gather. The stars remain steady but soften at the edges as scattered light picks up. You ease back up. The sharpness returns, and with it, a sense that you can measure time by the twinkle or by the lack of it. There is a rhythm to this, like breathing with the sky. The planet under you holds its color with calm confidence. Hydrogen and helium make the bulk of the air, but they are not responsible for the hue. Methane acts as the editor, cutting red light from the mix and letting blue reflect back. The high-altitude haze adds texture, sometimes shifting tone, sometimes clearing. The result is a blue that comes from chemistry and cold, not from any simple dye. The calm surface you see is the top of a much deeper story. Your ship glides through a corridor where light scatters the least, and the feeling of crispness peaks. A faint star near the limb of the planet stops shimmering and becomes a needlepoint dot. You can sense the low-glare geometry at work. When light doesn't bounce around, you stop fighting it. Your eyes stop correcting for flare. The effort melts away, and the view steadies like a lake at dawn. You test the panel brightness again, dimming to the edge of legibility. Your pupils open a little more. The starfield tightens another notch. Thoughts quiet under simple numbers. Less solar power means fewer reflections. A thinner haze means less scatter. Methane's red absorption deepens the blue and trims the stray warm light. Each factor leans in the same direction, and the effect stacks. The blue is not paint. It is the shape of light, after matter has made choices. The cold aids those choices, keeping methane present and haze particles small and sparse at this height. What you feel in your vision is the outcome of those quiet constraints. The stars look sharper because so little stands between you and them. You let that answer settle. Lower solar brightness sets the stage. Methane filters the warm wavelengths. The thin upper haze scatters minimally. The result is high contrast and clean points of light. The sky here honors edges. The blue veil opens. Now step into the air that makes it. What turns hydrogen and helium into sapphire from afar? You float where the blue holds steady, and you look into the mix that makes it. Most of Neptune's air is simple and light. Hydrogen and helium fill almost all of the volume, with a small share left for other gases. Methane is the key dash in that blend. It is scarce by percent, but powerful by effect. In daylight near a world like this, small ingredients do outsize work. Hydrogen and helium do not add color. They let light pass. They spread it a bit, but they do not shape the hue your eyes meet. That raises the question sitting right in your view. Why does a planet built of colorless gases present a deep, steady blue? The answer runs through chemistry that edits sunlight and through high layers that add a veil just thick enough to nudge tone without drowning it. Methane does the main editing. Sunlight arrives with a full spread of wavelengths. Some of those wavelengths hit methane and do not come back out in the same way. Methane absorbs strongly in the red and near infrared, removing much of the warm light between about 600 and 900 nanometers. Take those bands out of the mix and the reflected light leans toward shorter, bluer wavelengths. You see what is left after the cuts. The planet does not glow blue on its own. It returns a filtered spectrum that your eyes read as blue. That cut across the warm end is not smooth. It follows specific absorption bands where methane's molecules take in photons and transform their energy into internal motions. Those bands cluster through the red and stretch into the near infrared. So the light that would have filled the scene with rusty warmth never climbs far. The haze and clouds reflect some light back before methane can grab it, but much of the red tries to pass through gas layers first and gets trimmed. The result is a blue that feels quiet because the bright, warm wavelengths are muted from the start. Above the deeper weather lies a layer that fine-tunes the shade you see. The upper troposphere houses thin hazes and, at times, small methane ice clouds that sit high and cold. These cloudlets and veils act like small mirrors when the angle is right. They reflect some sunlight before the methane gas below absorbs it. That gives you bright streaks and spots standing against a darker field, especially in the near infrared. When you move across the limb, these tiny clouds wink in and out, not because they vanish, but because their reflectivity depends on how your line of sight meets their flat faces and edges. Recent near-infrared views have shown that high-altitude methane ice clouds can map out broader patterns, including a subtle bright band at the equator. That band hints at a circulation loop that pushes air down near the equator, warms it, and alters the light you see. Air that sinks tends to clear out haze and shows more emission in the infrared, which can make the equator glow faintly in those wavelengths. In visible light, the band is not as bold, but it still affects tone. Even a small change in cloud cover above the absorbing layers shifts how much blue reaches you without red mixed in. The haze itself is not uniform. Tiny particles form and settle while others rise from deeper layers. When the haze is very thin, the planet looks darker and the blue deepens. When the haze thickens, the color can pale a little because more light is scattered back before methane filters it. You sit at a level where the haze is light enough to let the methane do its work, but present enough to add a soft, matte finish. The balance can change with latitude and with time, and you sense that the palette is alive even while the scene looks calm. Think of the layers as stages in a filter stack. Sunlight comes in broad. High clouds and hazes reflect a fraction back out, often as pale highlights. The light that goes deeper runs through methane-rich gas that saps the reds and near-infrared. What returns carries a lower share of warm light. Your eye, tuned to contrast here in the dark, reads that as a saturated blue. All the while, hydrogen and helium provide the bulk medium but stay quiet in the color story, adding little beyond a slight scattering that smooths edges. When you watch long enough, you catch how the cloud brightness and spacing can shift the exact tone by degree. Where high methane ice clusters are dense, the planet's face shows more bright flecks. Where the haze thins, the base blue deepens and the highlights fade. Across the equator, the faint band adds a lane of subtle contrast that tracks the slow lanes of rising and sinking air. The blue is not one value, it is a field of values that move within a modest range, slowed by cold and distance. This color is the calm surface of a deeper system. Below these high layers, weather works on longer timescales and larger scales, mixing gases and building storms far under your path. The upper haze sits like frost on top of a dynamic deck you cannot hear and can barely see. That distance between the tone and the motion gives the planet its quiet look. The true activity lives beneath. So the answer settles into a simple pair. Methane sets the spectrum by removing red and near-infrared light. High-altitude hazes and methane ice clouds adjust the reflectivity and the fine shading you perceive. Together they produce the signature sapphire that carries across space. Hydrogen and helium are the stage, methane is the editor, and the haze is the brush that softens the edges. Hold to that clarity as your craft drifts on. The color is set. Now listen for motion in a place where no sound can travel. How to 2,000 miles per hour, winds become a lullaby you feel but never hear. You ease the craft into a glide over the blue, and the readouts note fast jets far below. Neptune holds the record for sustained speeds, yet inside your insulated hull, the world stays quiet. The ship's skin is a buffer, the cabin a calm pocket. Outside, momentum tears across latitude bands. Inside, time slows to the pace of your breath. High speeds suggest chaos. Your mind expects a roar, buffeting, and rattle. Instead, the hull murmurs in a slow cycle. That mismatch invites a closer look. The upper atmosphere here is thin, and flow can smooth into layers that shear past one another without breaking. Where the air is sparse and temperature gradients are gentle, the motion organizes into broad, steady streams. Turbulence folds in deeper down, where denser gas and strong contrasts carve storms, eddies, and the shifting boundaries that stitch banded worlds together. Up here, you ride the skin of a moving giant, not the scramble that churns beneath. The old flyby data still guides expectations for this air. Wind fields measured across latitudes, mapped jets that swing westward and eastward in stacked belts. Near the mid-latitudes, speeds climbed toward the extreme, and dark vortices traveled with them. That great dark spot was a high-pressure system, a void in the cloud deck where the flow wrapped like a river whirl. Features like that rise and fall. The jets remain, tied to temperature contrasts and the slow forcing from heat below. Even when storms shift or vanish, the conveyor persists. Your craft skims the top of this conveyor, a few kilometers into the haze, and the distinction between laminar slide and turbulent tumble matters. In laminar flow, thin layers slip past with minimal mixing. Pressure changes arrive as smooth waves. The hull registers them as gentle flexing rather than rattling hits. The insulation and structural frames soak up the high-frequency raggedness. What makes it through is a low beat, a long swell, then release, then swell again. In a vacuum, sound has nowhere to go. Pressure waves die at the wall, and there is no air outside to carry a roar to your ear. What reaches you must enter through the material of the ship itself. That means only the slowest changes, the ones that can move the frame as a whole, survive the filters of distance, structure, and damping. Fast gusts, sharp shifts, and small-scale chop damp out. The craft takes the edge off every jagged signal until the remainder is a soft, periodic rise and fall. You let the beat guide your breathing. The cycle ties to large-scale pressure differences across the hull as you cross gradients in the flow. Seconds lengthen into half-minutes. You feel two main notes, the planet's rotation carrying you over jets and the slow drift of your descent. Together, they write a calm meter. It is not the wind you hear, it is the ship reading the wind and translating it into a language your rib cage understands. Deeper down, the story changes. There, colder and warmer parcels meet with force, and the jets shear more sharply. Clouds condense along boundaries and break into waves. Vortices spin off the edges like eddies behind a bridge piling. That is where the speed becomes violent motion, where gusts punch and curl. Your path stays above that workshop. You watch the signatures in reflected light while avoiding the grip of their mechanics. The distance is your cushion. You pass over a latitude band where instruments have tracked rapid westward flow. The numbers hum on a screen, but the sensation remains steady. This is the paradox of scale. The air screams by at planetary speeds, but to the hull, the important quantity is the difference in pressure from one panel to the next. When the gradient is broad and slow, the ship flexes in rhythm. When it is sharp and noisy, the insulation swallows it. What you keep is the metronome, not the clatter. Storms dance below. Their tops drift and reshape, dark ovals forming and fading as energy moves through the deck. The bands slide under them as if they were on a conveyor. You do not hear any of it. You watch, and you feel the heartbeat against your shoulder through the seatback. A low thrum runs the length of the frame every so often, then fades, as if the craft is exhaling. Inside the cabin, gauges stay calm. Minor corrections tap the thrusters, then settle. The hull sensors log a spectrum of mechanical vibrations, but only the longest periods stand out to your body. Those periods become predictable after a while, and predictability is its own kind of comfort. The nervous system loosens when the pattern stays the same. The savage speeds below lose their edge at the surface of your awareness. The difference between sound and touch becomes clear. Sound needs a medium. Here, that medium is absent outside your walls. What touches you is structure-born motion alone. The vacuum separates noise from force. You receive the force in a softened form. rounded like stones worn by water, stripped of sharpness by the ship's ribs and braces. The idea that such winds could cradle you feels odd only until you notice how your own systems mirror the planet's. The internal heat that drives circulation down below is steady, not sudden, and that steadiness favors regular patterns. Those patterns repeat in wide, slow arcs, and at the altitude where you hover, they come through as pressure curves, not spikes. Your craft reads them, filters them, and hands you a pulse suited for sleep. Once you accept it, you lean into the rhythm. The hull expands a hair with a pressure rise, shrinks a hair as it fades. The seat carries that change to your spine. Your attention narrows to that touch. The faster events fall away. What stays is a slow tide. The pulse dims as you descend into a quiet blue chamber. Can lightning be bright and utterly silent? A faint flare answers you from the blue, a soft pulse behind the haze that folds and thins above the cloud deck. It blooms for a heartbeat. Then the dark returns, deeper than before. Another flash follows, farther off, stretched into a smear by layers of methane mist. You hold your breath and wait for the rumble your body expects. Nothing arrives. The cabin stays quiet. The silence is complete enough to feel like pressure in your ears. You track the source across the limb where the haze is thickest. Light passes through, scatters once, twice, and loses its hard edge. The color leans toward blue-white near the top of the cloud, then falls to slate and ink as the scatter fades. Lightning here lives under blankets too far below for any vibration to cross the void. The gap between you and the storm is not empty of light, but it is empty of sound. Thunder needs a path. Sound is a pressure wave that pushes air, and air is thin where you drift. Outside the hull, space cuts the line entirely. Even if a shock wave formed near the bolt, there is no medium to carry it this high. The flash reaches you because photons do not need a carrier. They cross the gap straight, or they bounce in the haze and arrive softened. The roar does not ride with them. Your mind wants a boom. Physics says no. Evidence for lightning on worlds like this comes in two kinds of signals that do not ask for ears. Instruments pick up radio spikes that match the signatures of electrical breakdown in deep clouds. Cameras catch optical flashes, brief and sharp when the atmosphere above is clear, smeared and faint when haze and cloud layers sit on top. From this height, you see the optical side, a flicker that rides upward through methane-rich air and leaves only a stain of light behind. The radio side would show up only on your console as a blip, a short burst that marks the time and place. The bloom you watch has a color that leans cooler than most lightning on Earth. Methane absorbs warm wavelengths on the way out, so the red part of the flash fades faster than the blue. What arrives at your eye keeps the colder edge. The effect lasts only a few tenths of a second. Then the haze eats the last of it. The dark that follows does not feel empty. It feels settled, like a pond that stops rippling the instant the stone sinks. You mark another pulse near the terminator. It glows in a vertical smear, as if a column carried the light upward for a short distance. The top fades from cyan to violet. Then it is gone. The shape recalls the way high-altitude electrical events can reach above storms back home, tall, fleeting, and quiet if you're too far to hear. That visual memory helps you read what you see now. A bolt fires in the depths, energy races into thinner layers, and a ghost of that path shows in the glow before the haze swallows it. No sound arrives. The cabin fans hum at their low setting. You notice them more because the sky gives you nothing to compete. Silence heightens detail. Your eyes work harder, and in that work, your mind slows. You begin to anticipate the timing, not by any schedule you can calculate, but by a feel for the rhythm of the weather below. Flashes group for a minute, then stop for several. The lull stretches. You keep watching anyway, knowing the next pulse will reset your sense of time. The mechanics behind each bolt begin with charge separation in deep clouds. Ice and other particles collide, trade electrons, and build zones of opposite charge. When the field grows strong enough, it breaks the air. A channel forms, current surges, light floods out in a burst. The haze above acts like fog on a window, turning a sharp spark into a soft bloom. That is what you see, clipped to the cool end of the spectrum by methane on the way up. The more you watch, the more the silence tells you what the place can and cannot do to your senses. Your ears are sealed from the storm by physics and distance. Your body still reacts, but to a different cue. Every flash narrows your focus, then the dark widens it. The alternation invites a slow breath in the light, a slow breath out in the dark. This is a world where energy moves without noise at your level. You let it pass through and past you. A long gap arrives. The haze takes on its steady tone. You watch for faint reflections on the underside of high cloudlets, the only sign that something deeper might be building. The calm stretches, then a brighter burst breaks the run, short, clean, and gone. If it had happened above an ocean on Earth, you would have counted the seconds to the thunder. Here, you count nothing. You simply wait until the scene restores itself to black. Light without sound sharpens the stillness. It trims away the extra and leaves only what your eyes can hold. You learn to read tiny shifts. A slightly wider halo means the path to the surface was a little clearer. A tight point means the haze was thicker and closer. No roar arrives to wash over those details. They stay distinct. You take one last long look at the dark that follows each flash. The quiet feels structural, like part of the planet's design rather than a pause between events. The storms work behind a curtain and send only light up to you. The vacuum and the thin air at your height keep the rest at bay. Your cabin keeps the boundary. The world outside remains hushed. Below the flashes, heat rises from a hidden furnace. How does a planet this far from the sun stay warm inside? You drift with the blue beneath you and feel a faint push from below, a slow press of energy that never arrives as noise. It climbs in long waves through layers of gas, patterns the weather above it, and sets a tempo that holds steady while the stars glide past. This is not sunlight at work. It is the planet's own warmth moving upward, quiet but persistent, shaping clouds and currents you can trace from orbit. At 30 astronomical units, sunlight is thin. Daylight here is a small fraction of what you know near Earth, yet Neptune's atmosphere stays busy. Bands shift, storms build, high clouds form and fade. The engine that drives that motion has to live inside. You feel its reach as gentle convection below the haze, not a surge, not a flare, but an ongoing lift that keeps the air in motion even when the sun contributes little. The source begins deep, where the planet still holds heat from its birth. When Neptune formed, countless impacts and compression warmed the interior. That heat does not vanish quickly in a body this large. It leaks out over long spans of time. Slow contraction adds to the supply as the planet's mass settles fraction by fraction and releases gravitational energy as warmth. There may also be a faint contribution from decay of radioactive elements mixed into heavier components, small compared to formation heat, but steady. You ride above a world that radiates more energy than it absorbs from the sun. The balance tips toward emission, and that extra interior power must cross the mantle and the atmosphere to escape to space. The flow is not violent. It is measured and broad, spread across the globe. You can watch its effects in cloud belts and jet streams that rely on heat contrasts to stay sharp. Without that internal feed, the gradients would blur and fade with time. Compare it in your mind to another ice giant that shows far less internal activity. The difference underscores how uncertain the physics can be in these deep, compressed fluids. Neptune's interior seems better at holding and moving heat up than its sibling, perhaps because of how materials mix at high pressure, or how layers slow the escape of energy. Whatever the exact cause, the result is clear in the atmosphere. Neptune's motions look livelier because more energy is available to move air. That energy moves through convection. Warmth from below makes parcels of gas rise. As they climb, they cool and can condense trace gases into clouds. Where air falls, it dries and clears. This overturning builds broad cells that feed the jets, sharpen boundaries between bands, and feed vortices that you can track for weeks. High above, you only catch the top of the circulation, but even that small part tells you the system is alive. Cloud features often align with where rising motion carries moisture upward to colder heights. Methane ice clouds gather along these lanes, bright in infrared views, and sometimes visible as pale flecks along the limb. Sinking regions can look darker because drier air allows light to pass into absorbing layers below before reflection. The pattern of bright and dark zones maps the conveyor that the interior heat sustains. You follow that map as your craft passes from latitude to latitude. Deep below, the pressure and temperature grow until water and ammonia enter exotic states that move heat efficiently. Interfaces between layers can act like lids, trapping energy until it finds a slow path out. Some models point to unknown opacity sources or complex mixing that cause heat to linger longer than expected, then bleed upward through channels that favor certain long-term rhythms. Those rhythms can set the pace of weather far above, even if you cannot see their exact source. You feel none of the rush that a hot engine suggests. The leak of heat is modest at any one place, but global and constant. The atmosphere responds by balancing. Convection lifts, radiation cools, jets transport, and turbulence down deep converts sharp gradients into smooth ones that then reform as the interior supplies more contrast. Over time, this becomes a cycle that runs without hurry, yet never stops. Instruments on board map thermal emission across the disk. Brightness temperatures shift with latitude and with time, marking where air is clearing or clouding. You note that regions near the equator can trend warmer in some bands, hinting at descending air that dries out and lets you see deeper. Mid-latitudes often carry the strong jets, where energy moving poleward or equatorward finds a balance and piles into fast streams. Each of these is a sign of the slow, steady interior push. That push also seeds the large vortices that come and go. When temperature contrasts sharpen, instabilities can roll up the flow into spinning ovals. Some drift for months before they weaken. When they do, the energy they held spreads out and feeds smaller features that the jets shear away. Through it all, the supply from within does not falter, so new structures have material to form from again. The warmth does not erase the cold, it meets it. Blue light from methane-marked layers sits above, while heat from inside rises below. The two interact at the cloud tops, where condensation releases latent heat in small bursts that reinforce upward motion. Each release is tiny, but many together build the patterns you watch. The contrast between frigid upper air and the slow interior glow gives the weather its shape. You settle into the idea that Neptune's heart beats, but slowly, no sudden pulses, no spikes. A quiet, steady output powers the circulation, sets up the jets, and keeps the cloud factories stocked. That is enough to sustain a living sky at the edge of sunlight. The layers between you and the core become stranger. What is the ocean inside an ice giant made of? You drift over blue cloud tops while far below, a mantle stretches for tens of thousands of kilometers, neither liquid in the way oceans flow, nor solid like a planetary crust. It behaves like a strange slush under crushing pressure and fierce heat. Water and ammonia dominate this layer, but they do not keep the forms you know. They reorganize into states that sound contradictory and yet remain stable in the deep. This is the ocean you never see, an engineered lattice of atoms with mobile parts, a conductor of energy, and a quiet engine for the world above. Call it a mantle, though it is not rock in the usual sense. The pressure climbs by gigapascals. The temperature rises by thousands of degrees. Under those conditions, water's structure changes. Oxygen atoms lock into a kind of crystal framework, while hydrogen no longer stays fixed. The protons slip through channels in the lattice, darting between sites, far more mobile than in familiar ice. That state is called superionic. It is not purely solid because parts of it flow. It is not a normal fluid because the frame remains. Ammonia mixes in and adds its own pathways for charge and motion, altering how heat and electricity move through the bulk. That difference from Earth's oceans matters. Liquid water at surface pressure transports heat by moving mass in currents. Solid rock conducts heat through vibrations and diffuses it slowly. This mantle does both and something extra. Ionic mobility lets it carry charge and heat in ways neither rock nor normal liquid can match at the same density. The result is a medium that blurs categories. It resists shear like a soft solid on short time scales, but can creep like a fluid over long ones. It transfers energy efficiently without needing fast bulk currents. It makes a slow world responsive. Under lab conditions that try to mimic ice giant interiors, materials like water show the switch to a superionic phase when squeezed and heated enough. Electrical conductivity rises. The lattice hardens, but the mobile ions keep moving. Within those boundaries, mixtures of water and ammonia behave differently than pure water, changing melting behavior and the ease with which ions move. Translate that to planetary scale, and you arrive at a mantle that can both store heat and feed it upward in broad, stable flows. The ammonia content plays a practical role. It lowers the freezing point and reorders hydrogen bonding, encouraging phases that support ion mobility at lower temperatures than pure water would require. In layered zones, ammonia-rich mixtures may remain softer, while water-dominated zones carry stronger frameworks. The boundaries between such zones can reflect or transmit thermal waves. Over time, these interfaces act like valves, letting warmth pulse upward or holding it back, depending on temperature and pressure gradients that shift with depth. In this slushy sea, thermal transport does not rely on violent overturning alone. Conduction through the supersonic lattice channels heat, while slow convection rides on density, contrasts set by composition and temperature. Convection cells may be large, with turnover times measured in centuries or more. Still, they deliver enough energy to the base of the atmosphere to keep the jets sharp and the cloud factories supplied. The mantle's capacity to conduct without churning prevents wild swings. It favors the gentle, persistent output you feel as a steady push beneath the calm blue sky. The same ionic freedom that carries heat can also carry current. As ions flow through distorted lattice corridors, they create conductive pathways, not everywhere, and not with uniform strength, but enough to matter. If the magnetic field of this world is born in layers offset from the center, it is because conductive flows take place in shells within this mantle, not in a compact metallic core. Tilted dynamos arise when electrical loops form away from the planet's geometric center and rotate with the body. A slanted field, a shifted source, and changing geometry follow from a conductor that is layered, mixed, and mobile in patches. Computer models of interior structure use equations of state measured and inferred from high-pressure experiments. They test how a water-ammonia mix compresses, how its conductivity rises with temperature, and how it transitions between phases. The results point to a mantle that hosts supersonic domains embedded in more fluid regions, separated by gradients in composition. Each domain adds or resists flow differently. Over depth, that patchwork sets where heat escapes easiest and where currents can loop. The outcome above is a magnetic field that wanders from tidy alignment and a thermal output that stabilizes without spikes. Think of how energy moves through this hidden sea. Heat forms or persists at depth, then climbs. It crosses layers that bend its path or slow it, reaches zones where ions carry it more readily, and finally warms the base of the atmosphere enough to start convection. The process is not smooth in detail, but it is reliable over long spans. Your altimeters do not tremble because of it. The signal shows up as a slow ground to the weather's wheel. The mantle does not roar. It hums through physics. The unseen ocean also stores energy. When the overlying layers cool slightly, this mantle yields heat back. When deeper zones warm, it absorbs some of that excess by shifting phase boundaries or accommodating more mobile ions. That storage capacity dampened extremes. It sustains a climate engine that thrives on small differences spread over large distances. The jet streams and vortices above trace those differences like ink lines on moving water. You are far from that boundary, yet you drift inside its influence. The warmth is steady because the medium below is built to regulate, not to surge. The mantle's mixed phases act as both blanket and conveyor, holding energy while also giving it routes upward where it can do gentle work. Every blue fleck in the cloud tops, every slow pressure wave against your ship carries a hint of that deep process. An unseen sea carries the whisper of heat upward. Extreme pressure and temperature force water and ammonia into exotic states that store and move energy with quiet efficiency. That is why the sky above remains active even when sunlight thins. Energy rising, magnetism bending, fields tilt the path ahead. What happens when a planet's magnetic field is tilted and off-center? You pass into a zone where your instruments hum at low gain, and the guiding lines you follow swerve away from the neat geometry you expect. Your path crosses invisible threads that do not point cleanly through the center. They lean, they wobble as Neptune turns. You find yourself correcting a degree here, a degree there, tracing a drift that feels like a slow roll applied by a hand you cannot see. Earth taught you to think of poles near the spin axis and a magnetic center close to the mass center. Neptune refuses that order. Its field tilts steeply from the rotation axis, and the magnetic source sits offset from the core by a substantial margin. The result is a lopsided dipole with extra structure riding on top. As the planet rotates, that skewed dipole sweeps space like a lighthouse beam that never points quite where the building stands. Your craft rides through the sweep and feels the periodic change as a recurring nudge. Voyager's past long ago mapped the basic facts that set your expectations now: a tilt on the order of half a right angle, and a center shifted from the planet's heart. That geometry means field strength can swing quickly with longitude at the same latitude, move a little around the globe, and you can pass from stronger lines to weaker ones without a change in altitude. Your magnetometers trace the rhythm, rise, fall, rise, each hour as the rotation carries the skewed field past you. Because the field is off-center, one hemisphere can hold lines that crowd nearer the planet, while the opposite side stretches lines farther out. Charged particles respond to those paths, racing along them, bouncing between mirror points, and finding easy routes into the atmosphere, where the field dips steeply. Instead of neat ovals fixed around the poles, the active zones shift with the sweep, and the curtains of charged particles glow where the lines guide them down. The effect is uneven and time-dependent, tied to rotation and to how the solar wind presses on the magnetosphere at that moment. Your sensors catch the coupling as the outer boundary breathes. When the solar wind strengthens, the day side field compresses and the night side tail stretches. In Neptune's skewed case, that compression can favor one local sector over another, steering particles into entry lanes that drift around the planet with each turn. Those entry lanes light the high atmosphere in patches that wander, not in rings that stay put. From your vantage above the haze, you see faint, shifting arcs at high latitudes that brighten and fade on a slow cadence. The field's tilt also turns otherwise straight trajectories into gentle curves. Your craft carries a small residual charge and a suite of conductive surfaces. As you cross regions where the field lines angle steeply, Lorentz forces nudge the motion by tiny amounts. Guidance compensates, but you feel the correction as a slow roll and yaw, subtle and regular. Even neutral paths bend indirectly. Plasma flows drag neutral gas in the thermosphere, which alters density and winds at the top of the atmosphere. Your descent passes through that layer, and the altered winds make the pressure you feel change on a rhythm set by the rotating field. You watch the pattern repeat. Near one longitude, the magnetometer climbs and the auroral monitors tick higher. A third of a turn later, they drop. Another third, they climb again, but not to the same value. The offset ensures that the two peaks are unequal because you are closer to the magnetic source during one pass than during the other. That asymmetry works its way into everything: particle flux, radio emissions, faint air glow, and the small torques your craft cancels to keep attitude steady. A tilted, off-center dynamo also alters the shape of the radiation belts. Instead of concentric shells, the trapped particle zones bulge and thin. Paths that would be symmetric in a tidy dipole turn into loops with kinks. As those particles scatter into the upper atmosphere, they heat patches unevenly. Local heating changes chemistry and can shift how quickly methane breaks apart and reforms in the rarefied air above your route. Small changes in composition at those heights affect how drag and lift whisper against the hull. The feel is not strong, but over minutes you sense the difference. A light hand on your shoulder that moves from one side to the other as the planet turns. The source of the tilt likely lives in the conductive shells you can only infer from above. Dynamo action in layers of superionic and ionic fluids that sit away from the center produces a field that lacks central symmetry. That geometry makes the field more sensitive to rotation, so it precesses and presents different faces to the solar wind every rotation. The coupling between the skewed field and the wind becomes a slow duet that writes the timing of auroral brightening and of the magnetosphere's breathing. You read the duet in the soft data scrolling down your screens. All the while, the effect on your body stays simple. The ship rolls a degree, then eases back. The route ground speed varies by a small amount, then returns. A slow meandering drift replaces straight line fall. That meander does something useful. It breaks monotony without adding stress. The nervous system relaxes into regular, low variance movement. Your eyes settle on the limb. The blue edge wavers by a few arc minutes and then holds. The invisible hand is not rough, it guides. You pass into a sector where the field lines arc farther out before bending down. The auroral monitors calm, the roll lessens. Through the window, the blue stays steady, but the starlight near the limb gains a hint of shimmer as the upper atmosphere's winds shift with the change in energy input. The planet's magnetism has drawn a subtle curve into your path and into the sky itself. The payoff echoes in your breathing. The tilted magnetism sets a gentle sway, adds a slow roll to your drift, and threads your descent with a curve you can lean into. You let it carry you along the skew, not fighting the nudge, letting your course trace the field that is there, rather than the tidy one you learned first. Curving outward, a faint ring plane gleams. Why do Neptune's rings hide until you almost touch them? You ease into the plane and see almost nothing at first. No solid bands, no bright hoops, only a faint, uneven haze against the dark. You hold your course a little longer. A thin arc sharpens, then slips away again, as if the light itself is deciding whether to show you the outline. The planet's blue limb gives just enough contrast to guide your eyes. The rest is patience and angle. These rings are not grand showpieces. They are lean structures, dusted and dim, strung around the planet like almost forgotten threads. Their names carry quiet history: broad, diffuse lanes and thinner bands known as Gale, Le Verrier, La Selle, Arago, and the outermost atoms. Within atoms, the arcs keep their own names: Liberté, Égalité, Fraternité, and Courage, segments that glow briefly, then fade. You approach them not as bright ornaments, but as marginalia written near the edge of night. Rings should announce themselves. Around Saturn, even a careless glance sees the system. Here, the rules change. Low albedo means the particles reflect little light. They are small, many of them on the scale of dust to pebbles, and their surfaces are darkened by space weathering. Under weak sunlight so far from the sun, they send back only a small fraction. What light they do send back prefers to go forward, into the direction the light was already traveling. That forward scattering behavior hides them from most viewings and reveals them only when your eyes line up with the sun and the ring plane just so. You shift attitude a fraction, and the difference is immediate. Fine particles behave like tiny lenses. They scatter light strongly when you look along the sun ring observer line. Off that line, they go quiet. At high phase angles, the arcs brighten as if someone raised a dimmer. At lower phase, they dim until the background swallows them. This is not a trick of your equipment. It is the geometry of small grains in a thin sheet. Your instruments confirm the pattern with photometry that rises steeply when the phase angle climbs past a critical point. The arcs inside the atom's ring are the strangest part. They cluster instead of spreading around the ring, as if a hand gathered them and held them in place. The explanation lives nearby in the orbit of the small moon Galatea. Its gravity sets up resonances that shepherd ring material into confined lanes. Particles that wander feel periodic tugs that nudge them back, so mass piles into segments rather than smoothing into a full circle. You can almost sense the cadence in the data as you pass. A gap, a bright arc, another gap, another arc. Order imposed by a moon's steady pull. You move through viewpoints that past observatories used with care. Voyager 2 crossed this plane at close range and first resolved the arcs as discrete features instead of a smooth ring. Later, sensitive imaging from large telescopes in space caught the system again, showing the faint bands and the shifting look of the arcs across the years. When glare is low and the angle is right, structure appears: thin rings, embedded clumps, and subtle brightness variations. When the geometry is wrong, the same system almost dissolves into the background. Your eyes learn the behavior as you watch. Gale spreads as a broad, diffuse wash, easy to miss until you know its width. Le Verrier and Arago are thinner, defined lanes that respond quickly to phase. La Selle sits faint, a smear that strengthens only when you cross that sweet spot where forward scattering peaks. And atoms, the outer ring, carries the arcs like beads you can count when the lighting cooperates. You test angles, letting the craft yaw a degree, then two, and the arcs answer by winking in and out. The effect is mechanical, predictable, and oddly calming. You get close enough for the plane to become a place rather than a line. Dust motes slide by in numbers too small to see as individuals, yet enough to change the histogram on your sensors. The particle size distribution leans small, which reinforces the forward scattering dominance. Larger bits exist, but they contribute less to the glow per unit mass at these angles. Their presence shows up in occasional speckle-like flashes, then vanishes again. The rest looks like a matte mist wrapped thinly around the world. The darkness of the material keeps the rings shrouded until your path and the sunlight align. Low albedo means fewer photons return toward you under most conditions. Out here, sunlight is already weak. Multiply the weakness by the dust's reluctance to backscatter, and the rings vanish unless you nearly share the sun's line of sight. Even within the plane, higher phase angles can help, but too high, and the planet's own glow and scattered light from the haze off the limb start to interfere. You learn to thread the balance, just enough phase for forward scatter, not so much that background halos drown it out. Your movement writes a quiet light curve in real time: brighten, level, dim, repeat. Each change in viewing geometry shifts the contrast between ring and sky. You notice that the arcs never blaze, they only emerge. This system does not reward haste. It reveals itself when you drift and wait. That rhythm suits the rest of the journey. Your breathing matches the slow waxing and waning of the arcs, and the ship's gentle corrections feel like they are choreographed to the same beat. Galatea's role never leaves your mind as you pass another arc. Resonances are clockwork that does not need noise to prove it works. The moon's gravity repeats the same whisper at the same places in the ring, over and over, and particles learn the tune. The arcs you see are the chorus staying on cue. If the resonance vanished, diffusion would smear the arcs into a ring over time. Their survival speaks to a steady, subtle hand. A last change in phase, and the system nearly hides again. Turning away by a few degrees pulls the light out of your line, and the arcs fade back into the dark like breath erased from a window. You hold the view at that dim level for a full minute, so your eyes can memorize how little it takes for a ring to disappear. Then you tilt back into the alignment, and the arcs answer with one more modest lift, a final confirmation that geometry governs what appears. So the payoff is plain. These rings are invisible until you're close and the light and angle meet their narrow terms. Low reflectivity, fine dust, and forward scattering keep them quiet until you align with their rules. When you do, they appear not bright, but sure enough to guide your path across the plane and out again. Past the rings, a backward traveler awaits. Why does Neptune's largest moon orbit backward? You tilt your course outward and meet a cold light ahead. Triton, bright against the dark, moving the wrong way around its planet. Your path crosses the ring plane and rises. The moon grows from a point to a disk with a steady sheen. It does not follow the traffic. It runs counter to it, a quiet defiance written into its orbit. Large moons usually move prograde, the same direction their planets spin, because they form from disks of debris that share the planet's rotation. Triton breaks that pattern. It slides against Neptune's rotation in a retrograde path. That one fact signals an origin apart from the usual family line. You approach with that history in mind and watch the day side brighten as the phase angle shrinks. The light it returns is too clean for a world this far out to be dark. The surface tells you that fresh frost resets the reflectivity often. A capture story fits the motion. Triton likely began as a Kuiper belt body, a large member of the icy population beyond Neptune. Long ago interactions with Neptune's gravity and with a companion or passing body drained its energy enough to trap it. Once captured, Triton's path would have been elongated and inclined. Over time, tides reshaped that orbit. They bled energy away inside Triton and inside Neptune, shrinking the orbit, pulling it towards circular, and locking the Moon into a retrograde track that sits close compared to a typical captured object. That tidal work matters for heat. As the orbit circularized, friction inside Triton converted motion into warmth. The effect would be strongest early on, then fade as the orbit settled, but it could have driven geology in the Moon's past and may persist at a low level. You read that possibility in the surface. Few large craters, broad plains, and patterns that look like frozen flow. Even now, slow energy sources may move volatiles from place to place in cycles you can trace across seasons. Your view resolves a pale, high albedo surface. Numbers run through your mind, on the order of 70% reflectivity. Nitrogen ice covers much of the ground, with traces of methane and carbon monoxide frozen into the mix. Nitrogen frost sends most of the weak sunlight back toward space. The little heat that remains can still work at the surface, especially where darker residues settle and absorb more light. That contrast sets up hotspots just warm enough to stir nitrogen gas under a thin, translucent layer and release it in bursts, redepositing bright frost elsewhere. The reflectivity stays high because the surface renews itself. At this distance, sunlight is scarce, yet Triton stands out. The frost's brightness helps, but so does the way the surface is kept clean. Geyser-like plumes, seen in past close passes, lifted dark material that then drifted downwind in thin streaks. New frost later covered parts of those stains, restoring shine. Over years, the process keeps the disk bright from afar. Your instruments confirm the composition in the bands where nitrogen and methane ices show their signatures. The data matches the gaze, clean tones, cold chemistry. Triton's retrograde motion also tells you about stability and fate. Orbits like this cannot last forever at close range. Tides raised on Neptune by Triton will slowly pull the Moon inward. Over immense timescales, that trend points toward disruption or a ring system born from a broken Moon. For now, the path is steady enough to navigate. The sense of going against the flow is not a metaphor. Every pass over Neptune's equator, Triton meets the planet's spin head-on. You trace the line where twilight cuts across a plane. The surface near the terminator holds a fine texture, low relief broken by broad, smooth fields and shallow troughs. Very few impact features interrupt it. That scarcity implies resurfacing. In a world this cold, the agents are volatile ices and slow tectonics rather than molten rock. Nitrogen and other ices can creep at temperatures near their melting points. Even slight internal heat helps them flow over long periods, softening older scars and covering them with plains that look young. Your approach brings out subtle color differences. Near some regions, a faint blush appears where methane-rich patches add a different tone. Elsewhere, a darker cap suggests seasonal deposition of tholins, complex organics made by radiation acting on methane, later muted by fresh nitrogen frost. The albedo pattern is not random. It maps the cycle of condensation and sublimation under a weak sun and a thin changing atmosphere that grows when parts of the surface warm and shrinks when they cool. Dynamics models of capture outline the path from an irregular start to the present calm. A binary object passing Neptune could have been split, with one member ejected and the other trapped. Energy lost through tides and perhaps through interactions with a proto-debris disk tightened the orbit and flipped it into the neat retrograde circle you see. Each step would have heated Triton, loosening its interior enough to allow episodes of cryovolcanism. Today, even at a lower heat budget, the legacy remains in landforms with smooth boundaries and vent-like features. You keep your pace low to read as much as the light allows. Albedo around 70% does more than please the eye. It governs temperature. High reflectivity keeps peak surface temperatures low, even at local noon, protecting the nitrogen ice from wholesale loss. Instead, the moon responds at the margin. Slight warming at transparent slabs can build gas underneath. That gas seeks a route out. A pulse escapes. Frost grains fall elsewhere. Over time, the surface keeps its shine and its restlessness in balance. The payoff ties both the motion and the brightness together. Triton orbits backward because it did not grow here. It was taken in from the Kuiper Belt and then tamed by tides into a close retrograde path. It shines because a veneer of nitrogen frost, renewed by subtle cycles and occasional geysers, reflects most of the thin sunlight. Both traits point to a world that looks calm, with a history of motion inside it. You follow its arc across Neptune's night side and watch the limb trace a line that conflicts with the planet's spin. The surface breathes without lungs. What lifts dark plumes from a frozen world into thin sunlight? You drift above Triton's day side and watch a stain rise from a pale plain, thin as smoke, in slow motion. It climbs straight for a while, then bends with a high wind, drawing a faint line that crosses the terrain like a brushstroke. Another plume appears a few hundred kilometers away, lower and darker, then stretches into a long tail. Both reach several kilometers up before thinning into brightness and vanishing into the glare. At minus 235 degrees Celsius, eruptions seem impossible. Nitrogen should be locked down as rock-hard frost, yet the surface changes in front of you. The key sits in the ice itself. Parts of Triton's nitrogen cap are not opaque snow. They can form clear, or at least translucent, slabs. Sunlight penetrates this skin and warms the darker grains and dust trapped beneath. That trapped heat does not escape quickly. Gas begins to build at the base as the nitrogen there turns from solid to vapor in a thin film. Pressure rises, finds a weak point, and vents. What looks like a geyser is a pressurized breath of nitrogen gas, lifting fine particles into a column that the wind then carries downrange. Seasonal heating sets the stage. The sun is weak here, but over months it can shift frost from one region to another. When the polar tilt brings light to a cap, clear ice persists in patches and focuses energy into the subsurface. Dust acts as a collector and a valve. It absorbs more light than the ice, warms faster, and releases gas locally. Those same grains can gather below the slab as they settle after past eruptions, improving the trap for the next cycle. With each day of low, steady light, the base layer grows more pressurized until a vent opens. Then the surface writes a new line across its face. Signs of this cycle were recorded firsthand when a passing spacecraft saw active plumes that rose to heights of several kilometers and then drifted for hundreds of kilometers with the wind. The dark streaks they left traced the flow. The observed columns looked narrow at the base and fanned out higher up, matching the idea of a jet that hits a shear layer and spreads. From orbit now, your cameras catch the same geometry: a needle, a bend, a feathered tail. The air is tenuous, but it carries enough momentum to shape the plume. Triton's breeze at altitude takes the entrained grains and lays them down as thin layers across the plains. Where the tail passes, the surface tone darkens as fine dust settles. Later, when frost recondenses, fresh nitrogen brightens those lanes again until a new eruption writes over them. The patchwork of bright and dark gives you a map of recent activity. High reflectivity marks areas refreshed by fallout of clean frost. Subtle grays show paths where darker particles still sit on top, awaiting the next coat. Methane plays a side role that your instruments can detect. Tiny amounts mixed into the nitrogen frost can tweak how sunlight penetrates and how rapidly heat builds underneath. Methane-rich zones may tint the surface slightly and change the timing of venting. Some streaks show a faint color difference that hints at this mix. Over time, radiation near the surface can turn those traces into darker products. Fresh frost then buries them again, raising the overall albedo. That is why Triton stays bright even with recurring dust. The process keeps repainting the ground. You watch a plume start from its first hint, a small halo that darkens, then a line that goes up. The base region shrinks as gas clears dust from beneath the slab. The column gains height and steadies, a steady flow rather than a burst. Minutes pass. The top bends more as it reaches a layer with stronger winds. The flow thins. The tail lengthens into a moth-wing shape that seems to float more than travel. Then the column fades until only the downwind smear remains. Another sight lights up, offset by a few degrees of longitude. One by one, the sources rise and settle, each writing the air. The engine behind this pattern does not require deep heat. It asks only for a translucent roof and a dark floor. The pressure you need to lift grains and carve a vent is modest. Once the path opens, the flow becomes self-sustaining until the pocket cools or the base clears of dust. In that sense, Triton's geysers are less like volcanic blasts and more like a solar pump. The sun supplies the steady trickle of energy. The ice translates it into mechanical work. As the plumes run, they also manage the brightness of the world. When gas lifts grains and then they fall, the surface roughness changes. Fresh frost later smooths these patches and increases reflectivity, pushing temperatures back down. That feedback keeps temperatures near a balance point. On timescales of seasons, the cap migrates, growing here, shrinking there, carrying its stored volatiles to match light and shadow. Beneath the crust longer stories might be shaping the ease with which gas travels. Some studies point to the possibility of deeper layers, warm, perhaps even partially liquid in places at great depth, feeding flexible behavior in the shell. If pockets of more volatile material exist, or fractures cross old, weak seams, pathways can form and reform with the migrating cap. Whether or not a deep ocean persists, the shallow cycle you watch is enough to move mass and redraw the surface each year. You track 3 more plumes. Each one rises, bends, and writes a tale that fades at its far end into dust too thin to see. Your ship's shadow crosses a field still marked with older streaks, now partly covered by a bright film. The contrast is low, but it is there, a fresh cap reclaiming the ground. In the quiet, the action feels almost like breath. Intake as frost condenses where shade falls. Exhale as gas escapes where light pools under a slab. That cadence is the payoff. Sunlight passes through clear nitrogen ice, warms dark grains trapped below, and builds gas until a vent opens. The gas jets upward, lifting dust into a plume that the wind carries away. Later, fine frost settles back, renewing the high reflectivity that keeps Triton bright. The surface remains cold because it can reset itself. The plumes keep writing and erasing, and the moon stays young in appearance. Even here, the sun whispers across billions of miles. Can the sun's 11-year heartbeat reach Neptune's clouds after a 2-year delay? You hold your orbit and watch the disk change slowly, not in hours, but in years. Bands near mid-latitudes pale, then recover. High clouds gather, then thin. The tempo is unhurried and repeats with a patience that suits this distance. You mark dates, compare frames, and see a faint rhythm emerge in the blue. At 2.5 billion miles, the sun should barely matter. Daylight is weak, UV is diluted, yet the charts keep a stubborn beat. Brightness curves rise and fall with a span that lines up with the solar cycle, lagging by about 2 years. The delay is long enough to test your doubt. Then the pattern shows again. It is not loud, but it is coherent, and it holds across instruments and seasons. The mechanism begins with light that does more than light. Ultraviolet photons split methane high in the atmosphere. Those fragments help build hazes, tiny particles that form from recombining hydrocarbons and related products. When the sun's UV output climbs near its peak, more methane breaks, more haze seeds form, and the upper layers can turn more opaque. That extra opacity dims features below in some bands and brightens the scene in others where the haze itself reflects. When UV drops, production eases, particles settle or aggregate, and the sky clears a little. The chemistry runs at its own speed, and the circulation spreads the results around the globe. You study the lag. The sun pulses on an 11-year cadence. Neptune responds about 2 years later. That offset makes sense if you think in transport times and microphysics. Freshly made haze does not change a planet-wide view overnight. Particles must grow, collide, and drift. Winds must carry them from source latitudes to where they gather. Vertical mixing pulls material downward into layers where clouds form or dissolves them back upward into clear space. Each step adds weeks and months. Together, they sum to years. The lag is the system's inertia made visible. Data sets stitch the story together. Long-running images show global brightness waxing and waning in step with the solar cycle plus the lag. Independent views reinforce the same phases. You align the plots and see the troughs and peaks agree within the margin you expect for a world with weather. It reads like a quiet conversation across space. The sun speaks, Neptune answers 2 years later, and the exchange repeats. Photochemistry does not act alone. Circulation patterns decide where the haze matters most. Near the equator, descending air can clear the upper layers, revealing deeper, warmer emission in infrared bands and muting high haze and visible light. When the global UV swing favors more haze, that equatorial clearing competes with increased production. The balance shifts the brightness strip that spans low latitudes. Maps show that belt waxing and waning in a way that fits both the chemistry and the winds. Recent views in the infrared highlight these contrasts. The equator shows a persistent brightness in some filters, a sign of drier, sinking air. Mid-latitudes host bands where clouds pop up more often, marking rising zones. As UV production of haze adjusts the supply of small particles aloft, it alters how much sunlight scatters back at each latitude. A slightly thicker haze softens contrasts and hides deeper cloud textures. A thinner haze sharpens edges and reveals motion below. The change is subtle, but over a global disk, it pushes the photometry up or down by amounts your sensors can track. You follow the 2-year clock across the terminator, watching twilight reveal the high layers grain. When solar activity is higher, the limb takes on a slightly milkier line. When lower, it cleans up. The shift is not dramatic. It would be easy to miss without steady records. With records, it stands out as a repeating fingerprint. The delay tells you about vertical reach. UV breaks methane high, but the clouds you see form deeper. For the surface look to change, those upper products must cascade downward or influence nucleation points that seed cloud particles. That handoff takes time. Particles grow by sticking together or by condensing vapors on their surfaces. As they grow, they fall faster, reaching layers where temperatures favor cloud formation. There, they either brighten by adding cloud or dim by shading what lies below. Once the solar UV fades, the system unwinds. Fewer seeds form, existing particles settle out, and the sky clears a little until the next cycle builds again. You test the idea by tracking latitudinal phase differences. If transport dominates, some regions should respond before others as winds carry material along preferred paths. The records show small offsets that fit with known jets and overturning cells. Mid-latitudes adjust first in some cycles, the equator follows. The pattern is not identical each time, which hints at internal variability riding on top of the solar driver. Internal heat does not turn off. It adds its own gentle noise to the clock. Ground-based records extend the timeline, catching the broader rises and falls across decades. Space-based views add crisp snapshots, tying the trend to specific layers and wavelengths. Together, they support the same core result. Neptune's appearance tracks the solar cycle with a delay. The amplitude is modest, the consistency strong. Out here, small inputs matter because they act on sensitive levers: particle size, number density, vertical gradients that control how the disk reflects and emits. Think of it as a long, slow metronome for a long, slow world. The click is the sun's UV rising and falling. The response is haze and cloud changing Neptune's face 2 years later. The beat does not force storms into being. It nudges probabilities and shifts thresholds. Where a cloud would almost have formed, it now forms more often. Where a feature would have stood out, it now softens. The integrity of the rhythm comes from the many small changes aligning in time. The payoff is quiet and firm. Solar UV modulates methane photochemistry, which modulates haze and cloud on a delayed schedule. That delay reflects how particles grow, settle, and ride the circulation before they alter what you see. Across billions of miles, a weak signal still sets a cadence you can measure if you wait long enough. You let the beat run under your breathing. The pattern outside settles the pattern inside. The cadence is set. It matches the quiet within you. How does a tour of a distant giant slow your mind on cue? You start by aligning with what's already here. The hull gives you a soft pulse, steady as a dockside swell. You match it. In for 4 counts, out for 6. The lights stay low. Outside, the blue holds, and every 40 seconds or so, a silent flare threads the haze and dissolves. You let your gaze rest where a flash might appear, but make no effort to catch it. The rhythm comes to you, not the other way around. Your thoughts take their seat behind the pulse, then behind the long, quiet dark that follows each glow. You set the ritual in 3 anchors. First, breath to the wind pulses, a low cycle that travels through the frame and into your ribs. Second, gaze to the silent lightning, which offers a brief point of brightness and then gives you more darkness than before. Third, thoughts to orbital rhythm, the slow roll from the tilted field, the unhurried drift across latitudes, the return to the same landmarks with just enough change to show time passing. Each anchor is simple, each one repeats. Together they build a loop your body can trust. Restless minds resist quiet, even in darkness. They scan, rehearse, and jump tracks without warning. They respond to novelty, not calm. So you reduce novelty by design. You slow the narration. You lengthen sentences so your breath expands to fill them. You pick a sensory detail, hold it, and return to it on schedule. The pulse rises, you meet it. The flash fades, you drift with it. The starfield holds steady edges. You let your eyes rest just shy of focus. The point is not to force stillness. The point is to give the nervous system a track with clear rails and the right speed limit. You use pacing like a hand on a dimmer. Consonants soften, pauses grow by a fraction, and transitions land on predictable beats. When the breath wants to run, you lengthen the exhale. When a thought climbs, you answer it with a return cue. Hull, flash, roll, and wait until the urge to think hard spills away. You keep sensory focus concrete, the faint sway at the edge of your vision, the cool against your fingertips, the pressure of the seat through your spine. Each cue is stable and low variance. Each cue trades stimulation for predictability. Your mind lowers arousal when it has a firm anchor. Mindfulness traditions call it paying attention on purpose to the present moment without judgment. Practically, it feels like parking your focus on one thing and letting the noise pass without grabbing it. Attention anchored to the same few signals reduces the body's tendency to ramp up. Heart rate drifts down, muscles loosen. The startle response quiets because nothing sudden happens. Sleep arrives more easily in that lower state, not because you forced it, but because you stop feeding the loop that keeps you awake. You also change the input mix. Consistent, low-variance stimuli act like a gentle metronome. When sensory input stops jumping, the brain no longer needs to predict or defend against the next spike. The slow, repeated pulse of the hull and the measured returns to darkness do that work for you. They trim away the micro-surprises that keep you alert. With fewer corrections to make, the cortex cedes control. Autonomic patterns take over. The body takes the hint and lets its own slower clocks set the pace. You frame the journey as cognitive offloading. Internal noise needs a target. You offer it the planet's large, steady motions and the silence between events. Vastness carries your checks and lists because it never reacts. It only repeats. Each time a worry surfaces, you place it on the limb and let the limb slide it out of view. The scale outside promises you do not need to hold what you cannot change. The habit forms in minutes. See the thought, put it on the drift, return to pulse, return to gaze, return to roll. You set the light so brightness stays low and color leans cool without glare. The blue outside is not the bright, alerting blue of a screen. It is a soft, methane-edited blue with the red end trimmed. Decoupled from device glare and kept at low luminance, it carries no daytime wake signal. It reads as dusk for the nervous system, even though you ride above eternal night. Dusk cues tell the body it is safe to downshift. Melatonin rises when brightness drops. The brain accepts the message because your environment agrees with it. Each pass takes longer than the one before. You count not seconds but events. 5 pulses, then a breath check, 2 flashes, then eyelids to half-mast, 1 slow roll, then shoulders down. The gaps widen, the returns lengthen. You do not try to fall asleep. You let the cadence run and allow sleep to find you on its own schedule. The mind keeps a little watch at first, then recognizes a pattern it has no reason to resist. It stops asking what's next, because what's next is already known. You keep the language stable. The verbs stay in the present. The nouns do not chase novelty. The voice does not rise. Even when a plume or a lightning bloom appears in memory, you treat it as one more gentle change that resolves into the baseline. Distance helps here. A world this far out grants you permission to move at its pace. Nothing hurries at 30 astronomical units. Nothing demands. You match that, and your body follows. You feel the threshold. The jaw unclenches. The tongue rests on the floor of the mouth. The breath slides so quietly through the nose, you barely hear it. The eyes, even closed, hold to the last dim shape, and then let it go. If a thought reappears, you give it the same route out, to the limb, across the dark, gone. You do not chase it. You do not replace it. You let the metronome pull it apart and carry the pieces away. That is the payoff. The planet's slow cycles provide a scaffold. Your anchors, pulse, flash, roll, entrain your nervous system. Arousal falls. The need to monitor fades. The edges blur. Sleep arrives not as a drop, but as a tide. The tide rises, and you stop noticing where wakefulness ends. You remain adrift, a small, calm ember over a sapphire abyss. At the edge of sunlight, rhythm and quiet carry you home to sleep. You keep the anchors you learned, breath to the hull's slow pulse, gaze to the blue that never hurries, thoughts set on a gentle drift. Each return is simple. Each return holds. Come back to this path whenever the day grows loud. Let the distance absorb the noise. Place each worry on the limb and let it slide into dark. You do not need to hold it. The drift stays with you, blue, silent, and sure. You rest in that steady cadence, and the night accepts you without asking for effort.